All right, let's talk about smart agriculture. Today, we're going to break down what that really means by looking at the modern farm as if it were a living thing. We'll explore the incredible electronic technologies that act as its senses, its brain, and even its body, completely changing the game for how we grow our food. So, why do we even need all this tech? Well, to get it, you first have to understand the huge problem it's trying to solve. Just look at this data from Japan. The number of farmers has plummeted since 1990, and the ones who are left are getting older and older, with the average age now pushing 70. This isn't just a number on a chart, it's a real crisis. Okay, so with that pretty serious challenge in mind, here's our game plan. We'll look at the farm's eyes, how it senses things, then its brain, which is all about processing and communication. After that, its body, or the automation. And finally, we'll wrap up by thinking about what this all means for the future. All right, let's jump right into the farm's eyes. Now, before a farm can see anything around it, it needs to know something really basic, but absolutely crucial: exactly where it is on the planet. And that sense of location comes from something called GNSS. You've definitely heard of its most famous brand name, GPS, but GNSS is really the umbrella term for all the different satellite systems up there. This is the absolute foundation that lets any self-driving machine navigate a field without getting lost. So how does this actually work? Well, it's kind of like a process of elimination from space. One satellite signal tells you you're somewhere in a big circle, a second one narrows that down, a third can pretty much pinpoint you on a flat map. But here's the kicker for farming. That fourth satellite is absolutely key. Why? Because fields are never perfectly flat. You need that fourth signal to get your altitude and know your true 3D position. But you know what? For things like planting seeds in a perfectly straight line, standard GNSS just isn't accurate enough. That's where a technique called RTK comes in. It uses a base station right there on the farm to correct tiny errors from the satellites, and the result is an accuracy of about 2 centimeters. To put that in perspective, that's about the size of a 500 yen coin. Just wow. Okay, so the farm knows where it is. Now it needs to actually see what's around it, to tell the difference between a crop it wants to grow and a weed it needs to get rid of. This takes us into the really fascinating world of machine vision. And trust me, computers see things in a totally different way than we do. And here's the most important thing to get your head around. A computer does not see a green leaf. Not at all. It just sees a massive grid of tiny dots called pixels. And for every single dot, it only sees 3 numbers: a value for red, a value for green, and a value for blue. That's it. Every color in the digital world is just a simple recipe. So the logical next question is, if you want to find a green plant, you just tell the computer to find all the pixels where that green number is super high, right? Seems simple enough. But nope, it's actually a classic trap. And the reason is light and shadow. A patch of brown dirt that's lit by bright sunlight can actually send back a higher raw green value than a perfectly healthy leaf that happens to be in a shadow. It's a tricky problem that needs a much smarter solution. And here's that smarter solution. First, they use a process called binarization. It's a fancy word, but it just means the computer uses a more sophisticated way to analyze color to change the image to simple black and white, which makes the plants pop out. Then comes step 2, labeling. The software goes through and gives every single white blob its own unique ID. So now, instead of a chaotic mess of pixels, the computer sees object 1, object 2, and so on, and can start analyzing each one. Okay, we've covered the farm's eyes. Now let's move on to its brain and its nervous system. I mean, having all this data from the sensors is great, but it's totally useless if you can't send it somewhere and actually, think about it. The farm's nervous system, in this case, is 5G. You can think of it as the super fast digital highway that connects all the eyes and ears of the farm, all those sensors, back to the central brain. It makes communication across huge areas nearly instantaneous. Now, 5G is a total game changer for 3 big reasons. First, it has the speed and capacity to handle massive amounts of data, like high-def video streaming from a drone. Second, it has incredibly low latency, which means almost 0 delay. That's non-negotiable when you're controlling a robot in real time. And third, it can handle a huge number of connections at once, so you can have thousands of sensors all reporting back simultaneously. So where does all this data racing across the 5G network end up? It all flows to the brain. And today, that brain lives in the cloud. We're not talking about a single computer in the barn anymore. This is a massive, powerful system that can be accessed from anywhere with an internet connection. This cloud brain is basically mission control. It gathers data from every source you can imagine: weather stations, soil sensors, the machines themselves. It does all the heavy lifting, like taking hundreds of drone photos and stitching them together into one giant, useful map. And maybe most importantly, it boils all that complexity down into clear, simple insights that a farmer can pull up on their phone or tablets. Okay, so our smart farm can see its environment and it can think about what it's seeing. Let's get to the final piece of the anatomy, the farm's body. These are the machines, the robots, that actually turn all those smart decisions into physical action out in the field. To really appreciate this, let's just establish a baseline. A recent test showed that even a very skilled, very experienced human driving a tractor has a steering accuracy of about plus or minus 15 centimeters. And that's pretty good. Now check out the difference. A robot vehicle doing the exact same task, guided by that super precise RTK technology we talked about, has an accuracy of plus or minus 3 centimeters. That's 5 times better. In the real world, that means less wasted fuel, less overlap when you're spraying, and just perfectly straight rows, 24/7. But this brings up a really practical question. How does a tractor from one company work with a seeder from a completely different company? The answer is a kind of universal language for farm equipment called ISOBUS. You can think of it as the USB standard for the world of agriculture. What ISOBUS does is create true plug-and-play capability. But here's the really mind-blowing part. It enables something called implement-led control. This means the smart tool, the seeder for instance, can actually take charge and tell the tractor what to do. It can tell it to speed up or slow down based on soil data to make sure every single seed is planted perfectly. The tool is now the boss. So let's put all the pieces back together. When you assemble these high-tech eyes, this incredibly connected brain, and this ultra-precise automated body, a whole new vision for farming starts to come into focus. And this is the real takeaway. Smart agriculture isn't about any one single gadget. It's about how all of these different technologies, the sensing, the communication, the processing, and the action, are all seamlessly woven together. They create a single, cohesive, intelligent organism, one that's designed to meet the massive challenges of modern farming head-on. Which leaves us with one last big thought to chew on. As these technologies become more and more common, solving these deep-seated problems of labor and efficiency, are we just looking at the future of farming? Or are we actually looking at the future of our food itself?